thank you for joining my session. It's about high performance Java Cloud native apps. My name is Markus Kett. I'm CEO and co-founder of MicroStream. I'm also editor-in-chief of the JavaPro magazine in Germany and co-organizer of the JCON conference. And with my team, I've been working on Java development and database tooling since more than 15 years now. So we also worked on, spent many years on working on the Rapid Clips Java development environment, which is kind of like visual Java development environment based on Eclipse. And in particular, we spent many years in improving the JBoss Hibernate tools to make database development more simple and more convenient to accelerate database development for Java. But this talk is about Java Cloud native apps and microservices. And so more and more companies must manage more and more data. So we are collecting more and more data. So we must collect data, connect data, and search data, and in real time, and to accelerate database applications in practice, to keep pace of the modern use cases of industrial software. And this is the reason why we need super fast applications and run it in the cloud. And performance is most important for modern big data applications. In a study, very interesting, Amazon found out that 100 milliseconds in latency cost them 1% in sales. So this is very interesting, which means response time is very important in the cloud. So performance is very important, and of course, resilient systems to be available and to handle the huge workloads. So the cloud infrastructure is changing everything. So actually the entire IT is revolutionary changing. It started with conventional database data centers, where we're able to rent physical machines, or to buy physical machines, or to rent virtual servers. Then the cloud infrastructure came up, where we are able now to build horizontally scaling clusters by just by writing some lines of codes. So infrastructure as code, which enables us to scale up our applications, manage huge, massive workloads to elastic scale horizontally. And this is really revolutionary. And also virtual machines. It started with virtual machines that enables us to virtualization the physical machines to run more applications on one physical servers. Then the next revolutionary step were containers that now enables us to run isolated, containerized microservices on virtual machines. And all these revolutionary changes in IT, they cause to revolutionary changes in software development as well. And here we have the microservices. Here we have a monolithic application everything actually is simple. So simple architecture. Everything can be managed by some method calls. So this is actually super simple. Yeah, software development is simple. The runtime is simple. Deployment is simple. Testing is simple. And it's one big piece of software run on one single big machine. So this is the concept of monolithic applications. And now we are able with containers to cut our monolithic application into numbers of single micro apps, microservices. We call it microservices, and they run in their own container, run isolated on a container platform like Kubernetes. And the question is the traditional Java stack suited to run such applications, to run tiny microservices in the cloud and using the native cloud environment to build native application, cloud native applications with Java? And yeah, for a long time, this was not really clear how should this work, because we have some requirements for cloud native applications that are challenging for Java. And for instance, we need super fast startup times for microservices. So if a microservice is down, it should be able to restart in milliseconds. And it should be able to run only one single service in a container in comparison to running multiple big Java monolithic applications in a huge application server that runs on a big machine. And these modern cloud native infrastructure is built to fail, which means it's possible that that microservices crashes all the time, that containers crashes all the time, and they have to be restarted restarted again in as fast as possible to be available to provide a stable and high available infrastructure, for handling the workloads, not running in the problem that we cannot that our software is not available and to lose money, similar to Amazon. And the question is Java fast enough, or the database concepts of today fast enough to meet all these requirements? And with the application server, the traditional application servers, we have some challenges. It's because it's built for monolithic applications. It's built to run various numbers of Java applications on one single machine, and it's built to start once and perhaps run for 2 years without any downtimes. So startup time is not that important for us with the application server. And the memory consumption is very high. The entire environment feels very heavy light. So this concept is not really suited for tiny microservices that should start super fast and run only one single small micro application. So this does not fit together. The same or a similar problem we have with the Java virtual machine. It's the JVM is super fast. So some years ago, customers asked all the time, "Is Java really fast?" So I've heard Java is very slow in comparison to C or C++. But the answer is no. It's super fast. And it's because of our JIT compiler. So as soon as the JIT compiler is hot, its Java application is super fast. But the problem here is the warm-up time. So the startup time of the JVM is slow and the memory consumption is high. And this is also not really suited for microservice as a runtime. So we have challenges here. Then we have also challenges with persistence. It's because with microservices, there are some rules, and we have to think completely different in comparison to monolithic applications. And one rule is each microservice that stores data should have its own database. And as we saw today in the keynote of Adam Bean, using relational database in a cloud and connection pooling and so on, this is really expensive for only a small service. So, and the complexity is also very high, and actually object relation mapping frameworks, which are still the standard in Java, right, are very expensive and feel also a little bit heavy-weight for individual microservice that should be really tiny and responsible for only one specific task, have only some 100 lines of codes. So adding object relational mapping framework like Hibernate feels a little bit heavy-weight sometimes. So this is the reason why the vendors of the application servers, they changed their runtimes. So they now provide small and cloud-native ready microservice runtimes, the microservice frameworks, such as Helidon, Micronaut, Quarkus, Spring Boot, and this changes everything. Now it's possible to get a faster startup time. They are built to start slow, to be fast, to have lower memory consumption. And here is a big picture about the evolution of the application server or the Java runtimes. We have the two worlds, Java Enterprise or Jakarta E and Spring. The Spring map here looks really simple. The Java Enterprise world, it looks a little bit more complicated. Here we have the traditional application servers, and now the new standard is called MicroProfile. So MicroProfile defines the standard for the new cloud-native, ready, small runtimes. They also implement the MicroProfile standard. Is a similar standard like the Java Enterprise standard. And then we have the runtimes, the frameworks that implement this MicroProfile standard. And here we have, for instance, Helidon, Payara, OpenLiberty, and then we have the reactive frameworks that are built to be not to follow the standard, but to be more lightweight and even faster. Here we have Micronaut or Helidon SE, and as we can see, Helidon is a special framework because it's the only framework that provides kind of like two frameworks in one. So Helidon P follows the MicroProfile standard, and Helidon SE is a reactive framework. So now it's possible with these new runtimes to run only, this makes sense now, to run only one small service in a container. And now we have the challenge with our JVM, and now GraalVM comes in the game. GraalVM is a really interesting project by Oracle, and it enables us to do polyglot programming, so you can combine programming languages. I guess this is not that important for Java developers because Java developers mostly want to write Java code. But the interesting thing for us is it enables us to create native images. So when I heard it for the first time, so I couldn't believe it, because I write a program, a Java program, and then I can generate a native image that is as fast as C. So this was my my thought. Oracle says the startup time is more than or around 50x faster, and the memory footprint is around 5x smaller. That it's really incredible, and this is really a game changer. And now this enables us to build really super fast microservices that start super fast and run super fast. And then Java was back in the game, in the cloud native game. And as Adam said today, now Java is leading in the cloud, even because so it's more, in comparison to the other programming languages, more powerful. So we have much more functionality. We have great ecosystem. So and it's super fast in the cloud, and we can save money. But with GraalVM, there are also challenges. So a native image does not support everything we have in Java, and it's also challenging to build a native image. It's a little bit effortful. It takes time, and the interesting thing is, and not everything is supported by a native image. But the very interesting thing is the new OpenJDK project Crack. So here we use the common Java virtual machine, and to save startup time, the system state, the hot system state of the JVM is persisted, and when the container crashes and you have to restart the service, then the system state, the hot JVM system state, is reloaded, and this enables a much faster startup time. So I never tried it out, so it should be it's really interesting to check it out. I don't know if someone of you have experience already. The functional principle is really simple because, so I've prepared a simulation. So here is my hot system state, and I persist the hot system state by creating a snapshot. And when the container has to restart, then we read the snapshot and restore the system state again. Here are some numbers, and they look really incredible, much faster than traditional JVM. This could be also a game changer, and yeah, let's see what technology, which approach will win in the end. But for us, for Java developers, this is really great, great news. So we can use whatever we like and what fits best for our use case. So then we have serverless. Normally we run the microservices in containers, and they are managed by container platform like Kubernetes. So this is actually the standard. But with serverless, we can now run our microservices and deploy our microservices in a fully managed service, in a fully managed platform. For instance, AWS Lambda, that manage the complete infrastructure for us. And this is very convenient because so we don't have to care for any configurations or actually for nothing. So everything is provided by the cloud provider, and we can focus on business logic, on creating our microservice, and the serverless container platform does and cares for the rest. And so we have the components for that, native image, micro runtimes, and great programming language. And so this is serverless can be very interesting. It's suited, or a good use case is if you have many containers that are not used or only or do not run all the time. So then serverless functions can be cheaper as soon as your service has to run all the time, or then perhaps Kubernetes can be more expensive than in comparison to serverless functions like AWS and Lambda. Check it out. This is really also a game changer and simplifies software development, testing, and deployment. What's about persistence? Database development. So I've mentioned already database development with Java. With traditional persistence can be a little bit heavyweight and perhaps too effortful only for creating some small services that should store only some data. Perhaps we need a kind like micro persistence. We have further challenges with database programming in general. So for instance, in Java, we use objects for almost everything. And as soon as we store data, then we are using mostly relational databases, and relational databases and Java object graphs are incompatible. So this is the reason why we have various impedance mismatches here. So and this is the reason why we have to adapt our object model to the database model all the time. So this is the reason why developers mostly say they have to develop their business logic, their application around the database. And actually, this is not really convenient, and so it's linked to limitations. And it's because the object model is can be much more granular than the relational model. And also, inheritance is not supported by relational model. With an object graph, for instance, we can navigate through an object graph very, very easily. This is not possible in the relational model. Here we have you will need a query language like SQL. The problem here is the more joins we have, the slower the query will be. In comparison to navigating through an object graph, this is mostly super fast. Everything is executed in memory. And we talk about microsecond query time. And also the data type differences. So most databases support more than 30 different data types. In Java, we don't have that much number of data types. So this is the reason why we need a mapping between the application and the database. And yeah, you can read about this in the internet. So find numbers of articles about object relation mapping and impedance mismatch. And with the NoSQL databases, pretty much the same. So there are all these databases out there. No matter which database you use, they provide all their own database-specific data structure or formats. And all of these structures or formats are incompatible with Java objects. So this is the reason why we need, in any case, a mapping between the app and the database, either an object relation mapping or a data conversion, for instance, JSON conversion. And by the way, it's through every single read and write, and this leads to expensive latencies. And really, milliseconds count. So we saw that slide that Amazon found out 100 milliseconds latency costs them 1% in sales. So this is really, really expensive, but nobody cares. It's because it's the job of the database vendors, right? So they should care for performance, but nobody measures the delay. So how long does it take to to convert data or object relation mapping. So we measured the time, and so even when we read the results that's directly from a local cache, then we were really surprised, because here it sometimes takes milliseconds also to read data directly from cache, and this is not that really fast. So the architecture gets more and more complex, and to improve performance, we are used to using memory computing. So actually, in-memory computing is used almost everywhere. So it's used in hardware. So hard disk use in-memory computing, database systems, they are caching data internally. And of course, in our systems, we also use in-memory computing. So why? Yeah, it's because that's clear. So we have some numbers here. In-memory computing is super fast. So mostly when we have access to memory, then we talk about sometimes nanoseconds. So assembler instructions are executed in nanoseconds. Mostly when you have access to memory, it takes microsecond, at least microseconds. When we talk about query time in terms of databases, then we talk about milliseconds, and the difference is 1000x. And so this is the reason why, of course, we like to use in-memory computing. So let's add another layer here. So this is the reason why we use local caches. But our system gets more and more complex, and so when we think about a tiny microservice, this can be a little bit heavyweight. So these are the challenges of database programming in general. Can we do it better? There is a concept. It's called system prevalence, and we can remember the project, the OpenJDK project Crack uses the same principle, and it's because we just store the system state by creating a snapshot. And so this is a simple concept, and we can do this also with data in a microservice. So we have here the same architecture, the same picture. So we now have our entity objects in the memory, our object graph, and so with creating a snapshot, it's super simple to store the system state persistently on disk. Super simple concept. Pure Java, no more mappings, no more data conversion. So here are the benefits, here are the pros. Then we can keep the system state in memory, then we can query and search in memory with streams API, so everything is provided by Java. This will be super fast. We have parallel streams even, and can really maximize the speed of in-memory computing with pure Java. Great. Looks really great, but unfortunately there are many cons, or even more cons than pros. And this might be the reason why this concept does not work in practice. And by the way, in my last session, there was an attendee that wrote in the chat, this remembers a little bit like to Prevailer. And that's really true. So Prevailer is an implementation of this system prevalence concept. And when we have a look on all these cons, then yeah, this might be the reason why this concept does not work or was not really popular in practice. It's because snapshots are expensive also. So creating a snapshot can take too much time. So storing the entire object state, system state. It costs also traffic on a network. Between the snapshots, you can lose data. And when we think about, we have to restart the microservice and have to to reload the system state, then this can take minutes. It depends on the database size, can take hours. So it's not suited for microservices. And yeah, memory is still expensive. So perhaps great idea would be simplify everything, but not popular in practice. With MicroStream, we solved all of these problems, and so we follow this concept and created a kind of like system prevalence 2.0, and then this concept becomes super interesting, and MicroStream is this is the reason why we call it a micro persistence layer, because of the concept is simple, it's super lightweight, and we have no requirements to the Java business logic or the classes. So MicroStream is a Java native micro persistence layer that runs within the same JVM process of your microservice, and enables you to store your object graph as it is in memory. And you can use all Java types, and it allows you only to store the delta, only the changed objects can be stored, which means you don't have to create the snapshot of the entire system state. You just store the changed objects, just store the delta, which is super tiny. So we create micro snapshots, if you like, and vice versa. It allows you to reload the object graph and restore it in memory. By using lazy loading, you can also load only subgraphs, individual subgraphs, and then MicroStream merges the reloaded subgraph directly into your object graph, so don't have to care for object copies. So everything is fully automated. Just call store or get methods. It's fully object oriented, so it's really convenient, and it's pure Java. And this is the only missing piece of puzzle in Java that is really missing, and everything else is provided by Java. And so we believe that this can be a game changer in data storage for microservices. It's super suited for microservices. And it's completely open source. So now we also open sourced the last lines of code, the database connectors. So everything is available on GitHub. So now the architecture looks very simple. We have the object graph in memory. We have MicroStream as a tiny Java library, and with MicroStream we can store the binary data into almost any data storage. So the obvious data storage is plain files, but blob storage are really suited to store binary data like AWS S3. We have connectors also to relational databases, because it's possible to store binaries with relational databases, of course. We have also connectors to Kafka or to in-memory data grids like Hazelcast. So almost all data storages can be used with MicroStream. The benefits are there are no more conversion, no more data conversion behind the scenes, no more mappings, nothing. So and we have no requirements to your classes. So we store all Java types. You can use pochos. You can design your object model completely freely. Yeah, that's super convenient. No annotations, no interfaces to implement. And this is the reason why we don't use Java serialization, and it's insecure, it's slow, and it's limited. So we have created a completely new serialization from scratch that allows you to deal with all Java types and to deal also with circular references. So you can, no matter how big is your object graph, how complex, circular references are supported, inheritance is supported, almost everything what's possible in Java. You can persist by MicroStream. And this is much more faster. It's because all latencies are eliminated. So to handle the same workload, similar in comparison to the JPA application, you need much lower memory. You need, I'm sorry, this is not true. You need much lower CPU consumption. So this is really incredible. So because of the performance of the JVM, so up to 90% lower CPU power with MicroStream. And this is the reason why we talk about microsecond search times. So because everything is executed in memory, so we search object graph as streams API, and we can reload object references with lazy loading. And what's also possible is if we like even more performance, input-output performance, then we can also use persistent memory to persist our data. And then this is much more performant in comparison to storing data, the binaries on a hard disk. This can be a really interesting approach, really to maximize your speed. And then you have almost pure in-memory power. I would say this is unbeatable. So here we have a performance demo. Two applications are running in parallel here. So we have one application is built with Hibernate and EH cache, and here we have a hot EH cache. Here we see the queries that are executed, the query code. So there's really no magic. We have 250 gigabyte data around, and we use an Oracle database as storage. And here we can see the JVM is mostly up to 100 times faster, sometimes more than 1000x faster. So this is actually not correct here. This is not the MicroStream performance. This is the JVM performance, because here we searching object graphs in memory. So we compare pure Java with Hibernate and the EH cache. Actually, EH cache, because here we have a hot EH cache. So we compare EH cache and the relational database with Hibernate with the JVM power, and only MicroStream is responsible for storing and reloading object references when they are needed in memory. And this performance is really possible with every Java application. So this is really not magic. So you can easily create such an in-memory Java in-memory application, database application, by writing plain Java, pure Java, core Java code. And the only thing is you have to find a way to persist your objects, and then you use MicroStream for that. And you get the same results here, unbeatable in memory power. And this is the benefit for your microservices. Then you have really fast startup time. You have super fast runtime with the microservice frameworks, and you have a fast and tiny persistence. Perhaps this does not fit for every use case. So it's your decision. Whatever you want to use, JPA, Hibernate, or MicroStream, you have the choice. You can have a look on the code. With MicroStream, you can see here I have POJOs. There are no annotations, no specific annotations with MicroStream, no interfaces, no superclasses, really clear, plain Java code. The object model, the Java object model, I think the Java object model is the perfect data structure, perfect data model. With microservices, we talk about multi-model. So with domain-driven design, we should design our services, and each service should be responsible for a specific task. And this is the reason why sometimes a microservice stores perhaps machine data, then a time series database would be perfect for that. Or you have complex data, connected data, then perhaps a graph database would be perfect for your as a storage. And perhaps sometimes, yeah, a document-based database is more suited. So with microservices, actually, you need multiple databases and multiple data structure. But when you think about the Java object graph, then with Java we can manage all. So it's actually the perfect multi-model data structure already. So you can store machine data, flat machine data. You can create super complex object graphs by these circular references and relations between the objects. You can store lists, you can use collections. So this is already the perfect data structure we have in Java. Great, fantastic. We can query it super fast with Streams API. What else? So it's in memory, it's optimized by JIT compiler, parallel streams. Great, fantastic. Try to beat it with any database. It's impossible, I would say. So the only thing is we have the only missing piece of puzzle is a way to store the object graphs. System prevalence is one approach. To persist an object, this is really simple in MicroStream. Just call a store method, but be careful, you have to store the owner object. So if you change an object in a collection, then you have to store the collection. And MicroStream does not store the entire collection, only the changed object will be stored. Each store is an atomic operation. So MicroStream stores the changes as a binary appended to your file storage. So it's a append log strategy. It's an all or nothing operation, so it's transaction safe, or it's comparable to a transaction in a database. When we load objects, then we can decide if the objects should be loaded automatically initially when the system, when the service starts, or you can define your object reference as lazy. So it depends on the use case. So if you need data instantly after system start, then keep it eager, so you don't have to do anything. Then it's automatically eager. If a fast startup time is important for you, then define your object references as lazy. Then MicroStream loads only the object IDs into the memory and nothing else, only object IDs. Then we have a kind of like fully indexed object graph. And as soon as you call a get method, then MicroStream loads the object reference into the memory. Imagine we use persistent memory, then even the load process will be super fast. Unbeatable fast, I would say. One of the most important questions is in terms of the system prevalence pattern is we keep the system state in memory, we keep all data in memory, so it means I need terabyte of memory. Okay, this is a really interesting question. Yes, if you want to have an in-memory database, you need memory, of course. So it's the same thing if you run a distributed cache or in-memory data grid, you need additional machines with memory. But with MicroStream, this is not mandatory. So if you have enough memory and you can load all your data in memory, then do it, go ahead. This will be super fast, you can't beat it. But if you don't have enough memory, or you have dramatic storage size, let's say you have tons of terabytes and you only have some gigabyte of memory, then you can use, as I mentioned before, you can use lazy loading, and then it's also possible with MicroStream, then define all of your object references as lazy, and MicroStream loads only the objects you call with the get method. Everything else is kept in a storage, and it's loaded on demand only. And you don't have to care for the memory management. It's completely done by the garbage collector of the JVM. So this is also really convenient. You don't have to do anything. You have fully control of your lazy references, of course. So you can define a timeout. For instance, if an object reference is not used for 10 minutes, you can kick it out of memory. You can, at any time delete your lazy references. Then it will be removed from the memory. And as soon as you call the get method again, then MicroStream loads the object reference again from the storage. So it depends on you. It depends on the use case. If you want to deal with bigger RAM sizes or smaller RAM sizes, as a microservice perhaps has mostly small RAM sizes. If you run bigger machines and if concerns of garbage collector pauses, then this should be not a problem, because you can check out the OpenJ9 JVM or Azul JVM, and Azul says they can manage up to 20 terabyte RAM size trouble-free without garbage collector pauses. So you can combine MicroStream with the with everything that's available in the Java ecosystem, and finally you get out a great architecture and great components to build super fast applications. Now with MicroStream cluster, we can now also replicate the object graphs through hundreds of JVMs. So that enables you to build distributed applications or distributed microservices if you need to scale horizontally and to flexible scale out and scale in your system based on the workload. So then you can do it with MicroStream cluster. That's pretty new. Tomorrow we'll introduce how it works, and you can elastically scale out, scale in your microservices, and they will be replicated automatically behind the scenes by the MicroStream cluster. So with these features, you can now build super fast applications or save tons of cloud costs. With our customer alliance in Munich, we had a project where we were able to save up to 90% infrastructure costs. This is really true. It's because of the performance of the JVM. So we had a cluster before, and now the application runs on only one single machine. This is not really true because it's high available. It runs on 2 machines. So up to 90% cost of infrastructure, this is really possible, and this will be more and more important to run and to build systems that save infrastructure costs. If anything is missing in MicroStream, then have a look on the great Java ecosystem. You can also use GraphQL to allow external applications to access your object graph in memory. If you need a better search, full text search, Lucene, you can use Lucene. And of course, you can combine it with all other technologies. So why not using, for instance, a search server like Elasticsearch and combine it with MicroStream, so everything is possible. So in the end, you have the choice. You get a great architecture with and the powerful infrastructure with Java as a programming language, with micro runtimes like Helidon, Micronaut, Quarkus, with a Java native image that starts in milliseconds instantly, and MicroStream as a fast, lightweight micro persistence. So great combination. Or just use Hibernate as your persistence strategy, traditional. So everything is possible. The most important thing is that we can build great applications with Java, and so Java is now back again in the cloud, and it's now leading. So these are good news. So if you have any questions, please feel free. There are no questions. Thank you for joining, and have a great night. Thank you.